And the title of the talk is The Role of the Star Clusters in the Dynamical Evolution of Their Planet. Dr. Flammini, please go ahead and share your slide.
Yes.
And you have 5 minutes for the question.
Okay. So I will just... Okay, can you see my screen?
Yes, perfect.
Perfect. Then good afternoon for you, everyone. Here is early morning. My name is Francesco Flammini Dotti, and I come from Heidelberg University, and I do my PhD in University of Liverpool and Zhenjiang Liverpool University in China. So today I'm going to present a little about how the planets and the star cluster actually affect those one, and therefore how they evolve in the meanwhile. So this is my outline. I will just talk in very short about the theoretical and computational background. So I will just illustrate how what are my tools in order to do the simulation that will eventually be used for determine how the star cluster environment affect the planetary system. And then I will present you about 3 works. One using a solar system inside the star cluster. The other one using an intermediate mass black hole on planetary system and free-floating planets. And then I will go through the effect of a global rotation on a free-floating planet and stars. So, what does it mean, planetary system and environment? So, because we know that most of the stars are probably formed from crowded stellar environments, we tend to say that we also have planetary system inside of those. And therefore, one of the studies that can be done in this is actually to use them for a range of the dynamic evolution of exoplanets in star cluster. And therefore, we basically create exoplanets in planetary system because we don't have found so many, as we will see in a little while. What we do is to model the effect on neighbor stars and the external galactic tidal field into this planetary system, along with the internal and external tidal potential that is given by the core of the star cluster and the galaxy that hosts the star cluster itself. We then see that intermediate mass black hole may be hosted in star cluster, so they're probably there, but we still don't have an effective visualized intermediate mass black hole in our observations. And then we use the global rotation that is seen and is demonstrated for a lot of star clusters. So, the total number of planetary systems that has been found in star cluster today is 27.1, in the sense that 27 are found in open cluster and 1 in the globular clusters. So, as you see, it's a very, very little number, even compared to the total number of exoplanetary systems that are currently found, that is around 6,000. What are free-floating planets? So, the definition is quite large, but in my case, I will say that a little shorter, in the sense that are simply planet mass systems that are not gravitationally bound to any stars. They can be not gravitationally bound to anything, but normally they gravitationally bound to either a galaxy component or they can gravitationally bound to a star cluster, like we consider in this talk. There is a lot of predicted free-floating planets. However, it's very difficult to find them because we need to check, we need to see which is the effective free-floating planets coming from. In our case, we see that the number of free-floating planets is this very nice number. This is because there are predicted, there are quite a lot, but it's difficult to observe them. But there are some studies, like Miretroic, in these last years, which found a large reservoir of around 600 candidates, which are still to be found as free-floating planets. So, then we say, why we analyze different environment? Well, of course, we have to first explain and obtain different architecture between planetary systems. It is important to understand how it actually evolved in order, for example, to have a population synthesis of planetary systems. We yet to understand the impact of those close encounters and how the environment itself, that in this case is considered a star cluster, eventually affect the evolution of those. And then we can go in more detail and nice evolutionary samples. So in this case, I will use a solar system in my first simulation, but for computational reason, I will rule out both Venus and Mercury. I will not use any satellite for our planet, and I will also rule out comet and asteroids. On the other hand, I will also use intermediate mass black hole inside the star cluster center, as I told you before. And then we will use globally rotating star clusters, like in this image from NASA. Now we'll go a little on the computational background, but know that this is an embodied simulation. I don't know how many are familiar with this kind of simulation, but basically is a lot of particles that are simulated in a way that resemble a star cluster. Therefore, this means also the density, the velocity distribution, and all the characteristics are related to that. The strong point of the code that I use is that it's very fast because it uses the GPU and MPI acceleration, where the simulation time becomes very, very fast. And what's more, we use also HDF5 storage that organizes data in a organized multi-planning data structure. For the first of the work that I'm going to present you, we use Rebound, that is a C-related code that is used to simulate, in this case, a little less number of planets, a very few ones, but is given with a very large resolution, and therefore it is relatively nice to use that. So the first one that this work is presented, you can have and you can do a photo of this if you like, is about the solar system scenario. So the solar system is a star cluster. The main research questions that I'm going to address here are related mostly to how the planetary stability is affected and how the planetary system architecture is dependent on the role of the Jupiter one. So dynamically, we know that planets can be scattered into more eccentric orbit, and this means that, for example, our solar system can be changed in its structure, basically. Jupiter mass planets, what's more, are relatively not perturbed by low mass planets, and this means, in our case, Earth and Mars. We also have secular and delayed perturbation, and we also know that solar system may be being close in a star cluster size. Let's give a little introduction in the initial condition parameters. So, as you see here, if you see my mouse, we have three different conditions for the number of stars and for the virial ratio. So the number of stars means that each of those have always the same dimension. So this basically is a different density for all the stars in the star cluster. As for the virial ratio, this is basically the division, the ratio between the kinetic and potential energy. At 0.4 star cluster with this value Q will be compacting, 0.5 will be in virial equilibrium, and 0.6 will be enlarging. A radius of 1 parsec, on the other hand, means that is a classic dimension for the star cluster, and then there are some initial mass functions that you may know very well from your studies. We have a Plummer sphere that is the classical for the distribution of a star in the star cluster, and we use the galactic data field that is fed by Earth in its position. Then, for the planetary system, we basically use the same configuration as the actual the actual solar system, and we use a certain number of planetary systems per star cluster depending on their density. And we evolve everything from 50 mega a year. So this one is the result of same major axis and eccentricity of the surviving planetary system in this model. As you see, the more external ones are more scattered. This is because the larger it is the same major axis, the easier it is for the star cluster to eventually encounter those and therefore scatter them into different same major axes. But as you see, we have these nice elements here of Earth and Mars that seems relatively unperturbed. This is why it is because Jupiter eventually treat them as a shield. This is the gravitational shield that does not make Earth and Mars be perturbed. But this is not always the case, as we will see in a little while. But before going into that, I'm going to describe this plot. Although it seems relatively difficult, it is not. So, on the right y-axis of the left plot, we have the cluster-centered distance. This means that this black line is the distance of the planetary system inside the star cluster into farther out. While on the left y-axis here, we have all the same major axis of the planet. On the right-hand plot, we have that the neighbor distance is given here in black as well on the right y-axis, while the left y-axis is the eccentricity. So this is basically the case in which nothing happens. And therefore, what you see is that there is no particular difference compared to field star, as it would be our solar system. And there is a normal evolution. Here, I basically do a zoom of the eccentricity in the first 5 mega year. And as you see, nothing of value happens. But let's say the extreme cases. So, what happened here with Jupiter? Jupiter in this case is the only planetary system that survives, as you may see. And it seems that a lot is going on. But the most important thing is what happened here. As you see here, there is a very strong encounter around 200 AU, distant from the star, and this would eventually eject the planets. If we do a zoom of only Jupiter in red and blue, green, our Earth and Mars, we immediately see that the ejection of this planet is due to Jupiter being inside their scattering area, and therefore they're ejected in a very short. Makes a very important understand of how the dynamical evolution of this kind of planetary system goes, because it depends on the architecture first, and secondly, it depends also on the mass of the most massive planet. But this is not always the case. In this case, we have basically that the star cluster basically kills the solar system. As you see, there is two encounters that eventually here eject all of the planets. But let's zoom like before the eccentricity plot, and we have to zoom again, and this is what happens. So as you see here, Neptune is immediately ejected, and the planetary system goes into a relatively perturbed orbit that seems to be stable after a little while, after let's say 0.01 mega years. However, we see that we have another encounter here that eventually ejects all of the planets instantaneously, and this is normally a very important factor, because it's very difficult to destroy actually our solar system. And the fact that it happens here is a very rare find. I will illustrate it at the end of this first part. So, in here, instead, we have the escapers of planets from the planetary system. On the row, you have on every row you have the fraction of a planetary system escape from the different virial ratio star cluster, and on the column you have different number of star as densities, as I told you in the initial conditions. As you see here, the major ejection that the star cluster experience is in the Q equals 0.5 and equal 10,000 stars. And this is due to time. Although this is a star cluster that is, the stars are a little more compact, on time the star cluster itself is more dense compared to the others. And therefore what we see here is what happens here. And we see that in majority of cases, Uranus and Neptune are the ones that are ejected the most, followed by Saturn, the terrestrial, and Jupiter. That is normally the most resilient one. So we didn't go too much into detail for the sake of time, but there are also the other important parameters that are the effective strength of the encounter and the star cluster relativity velocity of encountering star. The density, however, seems to be the most important parameter in this ejection. As for the planetary system, we have that most planetary orbits are stable during the 50 mega year, and not all the encounters are catastrophic. We expect all the planetary system that eventually lose planet to be stable after a little while. Normally, it is much less than 0.1 mega year. And Jupiter, as you saw, is both a barrier and the structure irreparably perturbed. And finally, we have that a lot of planets actually survive. So the planetary system is actually very resilient in a star cluster. And we have that the loss of planet is actually a smaller part of the whole together. So now that we've finished here, we can go into the intermediate mass black hole. So like I said before, here I also add free-floating planets and the planetary system with one semi-major axis. So I will go very, very fast over this, but know that an AMBH in stealth has been found by the LIGO consortium and is of 160 solar masses. They range from 10 to the 2 to 10 to the 5 solar masses. And the stellar runaway collision are the most accredited formation site for the AMBH inside the star cluster. So I will go through the initial condition here. So you already saw this one. So the major difference compared to before is that, of course, we have an IMBH in the cluster center of 0.
Dr. Flammini, we're not hearing you. I don't know if you're hearing us. Yes, yes.
Okay, so where did you lost connection?
I'm not sure which slide. If you bring back your slides, we can tell you. I think before this slide.
Here?
And we went past this one here. Yeah, I think this slide would be.
Okay, maybe let's try from here.
Okay. Okay, so you have 20 minutes of your time left. Please go ahead.
Okay, so basically here I will go through the intermediate mass black hole in a star cluster. So basically speaking, here I will use both free-floating planets and use planetary systems, as you will see, and I will try to understand how the MBH eventually affects the ejection rate of both planets from the host star and from the star cluster. as a matter of fact, IMBH were discovered in the Rigon Consortium. They found that 160 solar masses black hole, and those black hole masses range from 10 to the 2 to 10 to the 5 solar masses. The stellar runaway collision is the less controversial origin for the IMBH, and is this one normally used. And we see about the quantum mass segregation. So these are the initial conditions. I will not go to the detail of the others that we already seen, but I will highlight that we use a mass of black hole of 0, 100, and 200 solar masses, and that we start the stellar evolution at 30 megayear because we have a black hole, so we want a more massive star to eventually become more of age. We use 500 single planetary system and 500 free floating planets that have all one Jupiter mass, while the planetary system have 1 to 100 semi-major axes that are distributed in a logarithmic uniform distribution. So we will have both free-floating planets and dynamical free-floating planets, in the sense that since we start with free-floating planets, we identify those as FFP, while the dynamical free-floating planets, the one that form from the ejection from the Earth star, will be called bound free-floating planets, as here. So this is just to illustrate how the star cluster eventually is affected by the presence of an intermediate mass black hole. And as you see, the radius, the ratio between the core radius and the half mass radius, they contain half of the mass of the star cluster, is relatively constant in the presence of a 200 intermediate mass black hole, compared to the one that instead has a black hole in it that goes into core collapse. So as you see, the core collapse is prevented due to the presence of the intermediate mass black hole. And this is important, as you will see, about the evolution of the stars and the floating planets and the planetary systems. So we go to understand how the fraction of ejected planetary system from the planets, from the planetary system, are evolved during this. And as you see, there is a very similar distribution, although the initial starting of before 10 megayear is actually quite different. And as we will see, this is an important factor in the evolution, because this usually mean that everything important for the contraction in the contraction phase of the initial phase of the star cluster is responsible for the ejection. In the other case, the evolution is relatively similar. As for the escaping object from the star cluster, I include also the free-floating planets, that were ejected from a star. And as you see, there is a relatively large increment of 0.03% for stars, and similarly of 0.02% for the planetary, for the free-floating planets. This is much important because it is the fact that although we don't have a core collapse,
You're frozen again. I don't know if you're hearing us or not hearing.
here I am again.
Yeah, thank you. May I suggest maybe if you turn off your video, it might stop the internet
So to
connection
remove
being.
the camera.
Yeah. Can you
Okay.
please try sharing again?
Okay. How much time do I have left?
You have about 15 minutes left.
Including the questions?
If you speak for another 15 minutes, we should have time for a few questions.
Okay. No, I should be able to. Okay. Let's try again. So here, you were here or here, more or less?
We're not seeing your screen yet. I don't know if you've already shared.
Yes, actually I did not. Okay. Now. Okay. So you already seen this?
Yes, thanks.
Okay, so probably this one.
Yes.
Okay. Yes. Okay, so in here, please just focus on the green line, the green columns, in which, as you can see, there is a different fraction of ejected planets from the planetary system. And the different columns means this different density of the star cluster, again with the same number of stars. And the row means different mass of the black hole inside. As you see, of course, the density is still here a very strong parameter, but there is also an important contribution for the black hole itself, which we can see much better here, in which there is a 0.02 fraction of free-floating planets that are created in the first 5 megayear. And as you see, this contribution is present everywhere. If you compare different masses of a black hole from the first row to the second row. This is actually a very interesting detail because it means that the black hole is eventually a very important part of the dynamical evolution of the planets. It's although it's more effective on injecting stars.
I don't know if you're hearing us, but your voice is frozen. Your video, your slides are frozen.
Okay, I say that maybe I will just close here the talk and have some question because otherwise it's getting a little.
Okay, thank you so much for staying with us so far in spite of the connection problems.
No problem.
We have a question for you.
Thank you very much for your talk. I just have two questions. One is about the observational point of view of this types of research. In the current situation, is it possible to check the embodied models with observational data? Because as far as I know, it's very difficult to see the planets in star clusters, even nearby star clusters. So what do you think?
Okay, yes. No, actually it's relatively impossible. So it's, I would say that you should make a distinction. So globular clusters are basically impossible because they are so dense. There are many problems in observations. And the one that was discovered was actually done with a time transiting variation, and is only possible due to the fact that the host star was a neutron star, and therefore a pulsar. In the case of open cluster, it is relatively easier, but we have a very low number of possible targets, and that is the main issue with that. But we already have 27, and we have found them both with radial velocity and transiting model. So I would say that it is quite possible to find. As to your first question, that was with the embodied models. The embodied models can reproduce basically any kind of star that is not a very dense globular cluster, like say Omega Centauri. There's quite a bunch of stars. But yeah, it's possible to recreate any star cluster.
Second question is stellar evolution on in your simulation?
Stellar evolution, you mean? So,
yes. Is it
yes,
on?
they
in
are
your
always
simulation?
present. Yes.
Ah.
We also
And,
have a paper that illustrates more deeply on this.
So can you estimate how much this effects, I mean, escapers, is because of dynamical effects or because of stellar evolution of massive stars? Can you somehow estimate? Do you hear me?
And I heard it. It was if we have stellar evolution. I answered yes. And we also have a paper that deeply illustrates on this. I don't know if you want to give a deeper question on this.
Maybe we can discuss later because it's too late now.
Okay.
Thank you very much.
Yeah,
okay.
Sorry about all these.
You're welcome.
Issues.
And thank you again for accepting my invitation for this conference.
Absolutely no problem. It was very useful. Bye-bye.